Next to limits, we can also define one-sided limits. And take, for example, the function f of x is 1 divided by x. When we take a look at the function, we see that the limit for f of x for x going to 0 is not defined. Why? Because the limit from the left side seems to go to minus infinity, and the limit from the right side seems to go to plus infinity. We have two distinct parts. If we approach with values smaller than 0, we see that the curve goes down until we reach minus infinity. If we approach with values larger than 0, so from the right of 0, then if we follow the curve, we move upwards until we reach plus infinity. In this case, the limit of f of x for x going towards 0 is not defined. So we have in this case a function which is defined on both sides of a limit point, in our case the point 0. It exists on both sides, but it does not have a limit if we move towards the point. So it is a function defined on both sides of the limit point a, but it does not have a limit if x moves towards a. So in this case, we will not look at a limit for x going towards a. We will look at what happens when we approach from one of the sides. So see what happens if we approach from one side and not from both sides. So this brings us to a definition of a one-sided limit, and you can arrive from the left-hand side or you can arrive from the right-hand side. If we arrive with values smaller, then we call it the left-hand limit. So the definition is very similar to the definition of a limit. The left-hand limit, or in short the left limit, is the following. If f of x is defined on an interval BA, so we do not have an interval around A, but an interval to the left of A, so it's only on one side of A, the side we are interested in. So the interval BA, it is an open interval, so sometimes we also write it with brackets as BA, two notations for an open interval. This interval is to the left from A, and if we can ensure that f of x is as close to L as we want by taking x to the left of A and close enough to A, so we move x towards A but on the left side only, then f of x moves towards L, then we say that f of x has the left limit L at the point x equal A, and then we write this down as the limit of f of x for x going to A, but from the left side, so its value is smaller than a, so we write a minus. This limit is equal to L. The definition for a right-hand limit is very similar. You just take values larger than a, so to the right of a, and you make the necessary modifications. So basically everywhere where you have left, you change it by right, and you switch the interval to an interval a to c with values larger than c. And in the limit notation, you write x going to a with a plus, because you are on the right side, you are on the side where the values are larger than a. We then have the following theorem, which is quite straightforward. The limit of f of x is L if x is going to a, if and only if the limit f of x for x going to a minus is L, and the limit of f of x for x going to a plus, so from the right side, is equal to L. So the theorem just says that the limit can only exist if both the left limit and the right limit exist, and they must be equal. So the left limit and the right limit exist, and they are both equal to the same value. Some small examples. The first one, take the limit for x going to 0 of the square root of x. Of course, you know that you cannot take the square root of a negative number. So the square root of x is not defined for values lower than 0. So the only limit that we can take here is the right-hand limit. We cannot plug in values smaller than 0, so we cannot have a left-hand limit. We can only have a right-hand limit. In this case, if we take the limit of the square root of x with values of x going to 0 but positive, then obviously this limit is equal to 0. Another one, so the limit of the absolute value of x divided by x for x going to 0. Here you have to be a bit careful, because for the absolute value you know that the function looks like this, so it's a straight line, but there is a bend, a corner in 0. And we see that the value is always positive. So what it means is that if you're on the right side, the absolute value, for example, of 1 is equal to 1. So it means that the absolute value of x is equal to the point x itself. If you're on the left side, the absolute value of minus 3 is 3. So the absolute value of x, if x is negative, is equal to minus x. And so to solve such a limit problem, you have to distinguish two cases. You have to distinguish a left limit, and you have to take also the right limit separately into account. So for the left limit, you know that this absolute value is equal to minus x divided by x, and then x to 0 with values smaller than 0. So this limit is always minus 1. And this limit is the opposite, so it's x divided by x for x to 0. This limit is always equal to 1. And so here we see that the left limit, we will write LL for the left limit, is different from the right limit, RL. And so because of the theorem, the left limit and the right limit are not equal, the limit cannot exist. And so the limit of the absolute value of x over x for x going to 0 is not existent. A similar problem is the limit for x going to 2 of the absolute value of x minus 2 divided by x squared plus x minus 6. You know that x squared plus x minus 6 can be written as x minus 2 times x plus 3. But you have an absolute value, so you have to distinguish between values smaller than 2 and values larger than 2, because the absolute value is around x minus 2, so the corner of the function will be in the value 2. So what we do is take the limit of absolute value x minus 2 divided by x minus 2 times x plus 3 for x going to 2, and that with values smaller than 2, and you do the same but with values larger than 2. So for the first one, you have the absolute value of x minus 2 divided by x minus 2. The values of x are smaller than 2, so x minus 2 is negative. So this gives me the limit of minus 1 divided by x plus 3 for x going to 2 with smaller values, which is minus 1 over 5. And the other one here gives me the limit for x to 2 with positive or with values larger than 2. The absolute value of x minus 2 over x minus 2 will be plus 1, because x minus 2 is positive in this case, divided by x plus 3, or plus 1 divided by 5. And also here we see left limit is not equal to the right limit, and so there is no limit. You have a left limit. The left limit is equal to minus 1 over 5. You have a right limit, which is equal to 1 over 5, but you do not have a limit. And then as a final example, take the function f of x. F of x is equal to the square root of x minus 4 if x is strictly larger than 4, and it is equal to 8 minus 2x if x is smaller than 4. We have two equations, so one for values smaller than 4, one for values larger than 4, and so we cannot take a limit of the general function. We have to split it up because we have no option. So the left limit is the limit of f of x for x going to 4 with values smaller than 4. So it is the limit for x to 4 minus of 8 minus 2x. If we then just plug in 4, we get 8 minus 8. So the limit here, the left limit is 0. For the right limit, we do the same thing. It's the limit of f of x for x to 4 with values larger than 4. So we have the other equation in this case. So it's the limit of the square root of x minus 4 for x going to 4 plus. We plug in 4 and we get the square root of 0, which is 0. So in this case, you see that the left limit is equal to the right limit. And so the limit of f of x will exist. So x to 4 is equal to 0. So we have a right limit equal to 0. We have a left limit equal to 0. Then the theorem tells us that the limit exists and is also equal to 0.